Okay, here we are. I think we're ready to go. Alright, so last time we started with Big O, and we're going to keep on doing that kind of stuff. We did a few tests, and Quicksort actually performed better than the Big O analysis will show, but actually that's not a terrible surprise. Quicksort does sometimes outperform its Big O analysis, but we'll show you why that is as well. Okay. So let's just review how Quicksort works in general, and then we'll move on to, say, Mergesort or something. So basically, Quicksort works by taking a list, and it breaks it down into 3 different buckets. Technically only it needs 2, but I usually throw the third one in just so that the pivot element has somewhere to go. So it throws anything less than element 0 into the less bucket, throws anything equal into the equal one, and anything greater into the greater one. And then what it does, so that's a single pass through this for loop, which is the size of the list, and then it calls Quicksort on the less list and Quicksort on the greater list. And then at the very end, it just sticks it all back together. Now this is 3 for loops, but you notice that the total number of operations that these 3 loops put together are going to do is only the length of the original list, because this bucket plus this one are all equal to the size of the original list. So that's basically that. Okay, so let's keep looking at stuff. So here we have, so let's analyze the Quicksort performance just a little bit. And so this is maybe Quicksort Analysis. Okay, so how does Quicksort perform? What it does is it splits the list into 2 or 3 sublists. Either way, it must scan the entire list. So basically what I mean by that is that this is an O of n process, right? Whatever the list is, it has to do that amount of time. So if n is equal to the length of the list, then it's an O of n process. O of length of list. Right, and so now, what else do we have to do? We have to quicksort a sublist, right, the less list, and we have to quicksort the greater list. So we don't know how much time this is going to take. We'll have to, since it's a recursive process, we're going to have to do a little bit of guesswork here. Well, not guesswork, but we're going to have to do a little bit more thinking as to how the recursion is going to perform. So once we do that, then we have the merge process, which is also O of n. So really what we have is that the total time that it takes to sort, right, a list of size n is going to be basically 2 times O of n, which is just O of n, right, plus O of 2 times O of Quicksort. And now here's where we get into the issue. Quicksort of what? And so we have to think of the different potentials that can happen. So this is this is where we end up with issues. So let me explain the issue to you. Right? What are the kinds of things that can happen? Let's say you have a list of things. Let's say you have, 1, 2, 3, 5, 8, and 9, and 10. Sure, this is a list. Okay, so if we quicksort this list, what's going to happen, right? So this is no longer, we're not really doing time analysis on this anymore. We're actually just thinking about what's going to happen when you actually quicksort this thing. And the answer is it's going to break it up into, so the equal list is going to be 1. The greater list is going to be all of this stuff, and the less list is going to be null, right? Or empty, or whatever you want to call it. So So you have 3 lists, one of them is empty, one of them is just the number 1, and then everything else goes into the greater list. Right? So then when you try to quicksort the greater list, the same problem is going to happen, right? This empty list is going to get quicksorted. That's O of 1 time, because if you look at our code, we check for empty lists, we check for lists being of size 1. So if it's a list of size 1 or it's empty, that's an O of 1 check. It's just a single if statement. So this is O of 1 over here. But what is this over here? Well, this is O of n minus 1, right? And so that's actually a problem here. We're kind of doing the worst case analysis for quicksort. But you know, right now we're just trying to think of all the different possibilities of what can happen. So this is kind of the worst case. And why is this the worst case? It's the worst case because when you do the second splitting, right, you'll end up with basically the same thing. You'll end up with an empty list, and then you're going to end up with a list just with the number 2 in it. Okay, just make a new one. It's really hard to enter the text mode there. And then the greater list is just going to, oh, I'm sorry, 2, not 3. There we go. So the second time we do a quicksort here, it's going to split off the empty list, 2, and then the rest. And so that's also a problem, because then it's just going to give us, from the original thing, it's going to give us an O of n minus 2. And you can see how this is going to go, right? It's going to give us O of n minus 3, O of n minus 4, O of n minus 5, all the way down to O of 1. Now, if you add up, right, remembering the fact that if you add up n plus n minus 1 plus n minus 2 plus ... plus 1, we're actually going to get, you know, n times n plus 1 divided by 2, which is O of n squared, right? And so the worst case analysis for quicksort is actually an O of n squared process. And the reason why is because here it's going to take n recursions to get all the way down to the bottom, right? So there's like, in here there's like, right, there's like n recursions in here. And each of them costs O of n, approximately, right? And so because each of them costs O of n approximately, and we have n recursions, we're going to end up with O of n squared as our total runtime here. And that's, the thing is that that's not great, because as we saw with selection sort last time, remember selection sort is the like find min sort, and then swap sort. So selection sort is also of O of n squared, and as the size of the list grows, your runtime will grow with that size squared. And generally that's a bad thing, because, you know, 10 squared is 100, right? You can live for 100 steps. You know, 1,000 squared is 1,000,000, and most computers can do, at least on average, they do about 1,000,000 operations per second, right, nowadays. So, at least in terms of like each program, you can generally estimate it's about 1,000,000 steps of your sorting operation per second. Sometimes it's, you know, more than that, sometimes it's less, but the point is it's around there. So you can live for 1,000,000. But then once you get to, that's like 1 second. But once you get to, say, once you get to sizes of lists like n is equal to 10,000, that's where it usually starts to be noticeable. And then, of course, if you do something like a list of size 1,000,000, right, 1,000,000 is 10 to the 6th power, so 1,000,000 squared is 10 to the 12th power, so that's 1,000,000,000,000, right? And so, you know, what is 1,000,000,000,000? If you divide that by 1,000,000, so you'll get another 1,000,000. And then if you divide that by 3,600, which is the number of minutes in an hour, you get that divided by 24. So I'm getting, if you do about 1,000,000 operations, you do about 11.57 days. of calculation for 1 million sized lists. Now, a million sized list is actually not the most impossible thing, right? So if we end up with a runtime of O of n squared, we definitely want to do something about that. Like, if it's possible, you know, some algorithms it's just not possible to improve, but some algorithms it definitely is possible to improve. So anyway, so the 10 to the 12th calculation, if it takes 10 to the 12th steps, right? And I'm using the term steps very, that could be lines of code, or it could just be like number of iterations through the for loop, something like that. Some estimation of the number of steps that the algorithm actually takes. If it takes that number of steps and you're doing about 1 million calculations a second, then it's going to take you about 12 days to finish on a million size list. So you're not going to want to do that, right? You're going to, if you're a human, you know, humans like things done a little faster. And so let's see what the better runtime is for Quicksort. So this is the worst case analysis of Quicksort. What is the kind of, yeah, let's call it the best case analysis of Quicksort. So let's think about what the best case is for Quicksort. And you notice that Quicksort is really quick. It actually looks, most of the time, you get something close to best case performance. And also, the other thing about Quicksort is that you get sometimes things that look a bit faster than n log n. So this is asymptotic performance, but sometimes you'll even get performance that looks kind of more like O of n. But anyway, so let's do the analysis now. So remember where we stopped off, and we had to say, well, we don't know, right? We said that the time based on a list of size n is equal to O of n plus 2 times O of the quicksort of something, right? And so let's go back to that, and now let's say, well, what is the something again? So we did the worst case where we split off one element to be in the equal list and the rest of them were in the greater list. Now this is, there's a lot of different worst cases, right? So you can always have maybe everything go into the less list if you have a reverse sorted list. If you have, so all of those things are definitely possible with Quicksort. But if this is our like fundamental equation here, that the time is equal to some multiple of the size of the list plus 2 times the time that it takes to quicksort the sublists, what's the best case for the sublists? So the best case for the sublists are equal splitting. And let me show you an example of that. So if we have something like, so we have 5, 10, 2, 8, 3, 19, 21, and 4, right? Then our first step for a quicksort is going to be, we're going to get, 2, 3, and 4 into the less list. We're going to get 5 into the equal list, and we're going to get 10, 8, 19, and 21 into the second list. Now I know that this list is already kind of sorted. This list is still a bit out of order, but who cares? The point is that what's going to happen is now it's going to quicksort this thing. It's going to quicksort this thing in a few steps. This one, it's going to, when it splits this one off, it's going to say that this one, 8, is in the less list, 10 is in the bigger list, and then 19 and 21 are in the bigger list. 10 is in the equal list, and then 19 and 21 are in the greater list. Here it's actually the worst case, but it's going to still work out okay. So we're going to have an empty less list. 2 is in the equal list, and 3 and 4 are in the greater list. So even though this one is not so great, it's okay because the actual number of steps here is not so big, right? We're almost down to single size lists, so it's okay that it's kind of doing the worst case behavior here. It really matters in the first few steps, right? If the first few steps split off and you have like 2 elements going into one of those sublists and like 1 million elements going into the other sublist, that's what truly generates the worst case behavior. And then you see here, I guess you would have an empty less list, a 19 in the equal list, and 21 in the greater list. And so when you combine everything back together, you get 19, 21, and then you get 8, 10, 19, 21, and then you get 2, 3, 4, 5, 8, 10, 19, 21. and then everything's sorted. So in the best case, we're going to get an equal splitting. So what we're going to do is we're going to put n divided by 2 in here. Okay? And so let's actually track to see what happens here. So basically what's going to end up happening is what should we say here? So I guess the way to think about it is you need to think about it as it splits. So yeah, so what we're going to do is we'll say that it's 2 times the O of the quicksort of n over 2, but that's also equal to, right, the original O of n plus 2 times O of n divided by 2, right, because I'm just using this formula within itself, right, the time of quicksort, so we can even replace this with t right here. And then what we're going to do is we're going to say that this is plus t, 2 times t of n over 4, like this. And then, so that is what happens after 1 splitting, or I guess actually after 2 splittings. And then what we're going to have here is something like this. We're going to have 2 times O of n over 2 plus 4 times t of n over 4. And so we're going to do this again. If we split again, what we'll see is we'll say that this is O of n plus 2 times O of n over 2 plus 4 times O of n over 4 plus, and maybe we should not use O, we should just use time for everything. Well, let's just use O, it's fine. But I'll pretend that we can absorb these constants into the big O, and you'll see why I'm going to do that in just a second. Well, you know, you'll get 8 times O of n over 8 plus, say, 16 times O of n over 16, etc., right? And now what we're going to do is we're going to say that, like, k times O of n over k is just equal to O of n, right? Now, you might say, well, that's technically a little bit misleading because the O should absorb the you know, whatever. So anyway, so the point is that here, the question, the real question that we have to ask, so this is a really complicated analysis, but the question we have to ask is this. How many steps can this possibly do, right? Right, so if you agree that the first time it splits we get an O of n over, or t of n over 2 or something like that, and then we get a t of n over 4, t of n over 8, t of n over 16, etc., the answer is we can only do as many steps as until n divided by 2 to the steps is approximately equal to 1, right? That's how many steps we can do, right? And now you might say, well, what's this approximate business? Who cares, right? So what I'm going to say is approximately 1 means somewhere between, say, 1 and 4 or something, 1 and 2, really. So, and that's how we know that we're not going to be able to split anymore. So what we need is we need to know, so we're going to do n is approximately equal to 2 to the number of steps, right? And what that means is it's somewhere between this and the number of steps plus 1, basically. I think that's the best way to analyze it. So 2 to the number of steps is less than or equal to n is less than or equal to 2 to the number of steps plus 1. And then all we have to do is really just take the log base 2 of all these sides. So we take the log base 2, lg of 2 to the number of steps, and that's just equal to the number of steps, is less than or equal to the log base 2 of n, is less than or equal to 2 to the, well, steps plus 1, right? So we know that the number of steps is somewhere between well, basically the number of steps is somewhere around this log base 2 of n, if we're in the best case. So if we're in the best case and we know we have log n steps, and each step costs us, how much does each step cost us? Look at it at the cost of each step. O of n, and then here's 2 times O of n over 2, which we're pretending is just another O of n. 4 times O of n over 4, which we're pretending is just O of n again. 8 times O of n over 8. Again, we're just pretending that's O of n. So each step is going to cost us O of n, right? And so if each step costs us O of n, and we have log n steps, then we just multiply log n times O of n, and we're going to get O of n log n. And this is the best case runtime for Quicksort. So basically, what you do is you kind of break it down into cases, right? In the worst case, you split off like one element into the equal list or maybe the less list or something like that, and the rest of it goes into the other list. So this is the worst case. The reason why I make the equal list is actually for these cases, because the problem that can actually happen, so here's a secret problem if you don't make an equal list, is that in your actual implementation, what can happen is you can end up with the exact same list being passed into the next step. If you don't split off the elements that are equal to the pivot, then you have to make a decision. Either they all go into the less list, or they all go into the greater list. And let's say that you put them all in the greater list. So then the greater list can actually be the exact same size as the original list. So in the actual implementation, if you don't split off the pivot, then either less list or greater list can be the exact same size as the original list. And so if you don't, at least you have to do some extra stuff to check for that. And so that's the issue with not having an equal list. So that's why, I mean, I kind of invented the equal list as a way to solve this problem, because I figured it was a way to like prevent the algorithm from malfunctioning. You can actually get an infinite recursion that way if you don't do that. So that's why we do this. Okay, so yeah, so basically the way to talk about it is that the best case of runtime for Quicksort is O of n log n, and the worst case is approximately O of n squared. And so there are ways to prevent, just to be clear here, there are definitely ways to prevent worst case performance from Quicksort. One way is that if your list is already sorted, you can just return false, and that'll fix one case. But if it's almost sorted, then it'll still basically be worst case performance. So another way to do it is that the general like standard accepted practice is either, instead of picking pivot equals element 0, you can pick pivot equals element random. So that's one way to do it. Or you can find the median element and use that as the pivot. Because if you find the median element, it will cost you some time. It will actually increase your runtime a bit. But if you actually bother to find the median, then the thing that it's going to do for you is it will ensure equal splitting of the list all the time. So it ensures best case performance. So element random is kind of a randomized way. It doesn't perfectly force you to get the best performance, but it's better than nothing, because if you pick a random element, you're probably going to it's very unlikely that you're going to accident your way into worst case performance, but that can always happen. So equal splitting of the list all the time is done by using the median element, and there is an O of n algorithm. So the important thing is that there's an O of n algorithm to find the median of a list. Okay, because generally the way you find the median of a list, so the secret thing is that it can be a little bit circular, because generally to find median, you sort, which is O of n log n, and then you pick the middle element, right? So that's like the easiest way to find the median in terms if you already have a sorting algorithm implemented. But you see that you can't actually use that if you you can't use that if you're going to do anything like this, because you need a better algorithm to do it. So the algorithm that does it is actually, it's a bit more complex. It's a it actually is a bit like Quicksort in itself, but it asymptotically runs with about O of n performance, which is what you need in this case. Because remember, the splitting operation and merging take O of n. So if you can get something else within O of n, then it doesn't give you any additional cost beyond the secret hidden constant. So, okay, so that's basically all that I want to say about Quicksort right now. So basically you have the best case and the worst case. So I want to talk about Mergesort now. So Mergesort is another, what we call, like, n log n sort. So Mergesort, not Mergesort, Mergesort is, I think, my favorite algorithm in terms of sorting. And the reason why it's my favorite is because it's very simple, and it's also, there's no randomness to it. It ignores the shape of the input data. And so that's, in my opinion, that always, it like speaks to my underlying, sense that I want things to be very deterministic. It's extraordinarily deterministic. It's going to do the exact same thing on a sorted list to an unsorted list. It doesn't really have best or worst case performance. Its best case is equal to its average case, which is equal to its worst case. So all cases are essentially identical, and and you'll see why in a second, is because it totally ignores the shape of the input data. And what I mean by shape is whether the data is already sorted. It doesn't care about that. It's going to do the same thing every time. So let's see how it works. So basically, here's how it works. You take a list, split it in half, and what I mean by split it in half is you literally take elements 0 up to size over 2, and that goes into the first list, and then you take size over 2, maybe, if this goes up to size over 2, right, so this is 0 less than or equal to I less than size over 2, so you take all the first elements, you stick it into one sublist, you take size over 2 less than or equal to I less than the end, and you put that into the other sublist. So there's no thinking that goes into this splitting, right? There's no thinking at all that goes into the splitting. And that's actually a good thing in a sense, because you see the Quicksort thinks about how it's splitting the data, and because it's actually thinking about how it's splitting the data, there are ways to make Quicksorts that perform really badly. But in this case, actually, it doesn't think for even a second about what it's doing. It just splits the list in half, and then it merge sorts each half, and you're like, wait a second. But then once that returns, right, once those two things return, then what it's going to do is it merges them back together. So this is where a little thinking has to happen. And so let me describe the merge algorithm that we need. The merge algorithm takes two lists and shoves them, I shouldn't say it takes two lists. It takes two sorted lists, merges them into a bigger sorted list, right? So merge sort requires you to implement another algorithm. And so let me show you that algorithm right now. Let's implement the merge part of merge sort. So let's return a vector int reference, or yeah, we can just return a vector int, and we'll just implement this as merge. This is not merge sort, right? This is specifically merge, which is some subpart of merge sort. So this is not merge sort. This is just the merge part. And so what we're going to do is we'll make this a reference so it doesn't copy. First list, vector int reference, second list, right? And so to merge two things together, what you're going to do is you're going to say, let's make, and then int second index equals 0, so we'll start with indices. And then I'm going to say while the first index is less than first list. Oh, I guess we should use unsigned. Otherwise, it's going to yell at us. But I mean, who cares, right? So first list.size and second index is less than second list.size. So there we go. So that's what we want to do, right? And then what are we going to do? So let's make our vector int result list, right? And then we return that at the very end. So what's going to happen? So basically we check if the element, so first list at first index, is less than, right, the second list at second index. Then what we're going to do is we're going to stick the thing, we always want to stick the least thing in first because we want to make this a sorted list. So what this is going to do is we're going to add the first list at the first index to our resulting list. So what we're going to do is we're going to say result list. This is not a very efficient way to do it, but the good news is Big O doesn't really care about this kind of efficiency. There's a lot of better ways to do it. Like for instance, if you did this with actual arrays, you could be smart about it and pre-allocate all the memory instead of pushing back, which could actually cause multiple allocations to happen in the result list, and definitely will cause that to happen. But again, we're not going for the best implementation. I'm just going for like the most understandable implementation of all these things. Okay, there we go. And then the last thing we have to do is do first index plus plus, right? Because the good news is once you've used that index, you're not going to use that index again. So else, oh, someone honked their horn. And if it's greater than or equal to, we're just going to take from the second list at second index. And then what we're going to do is do second index plus plus, like that. So this is what we're really going to do. Technically, we could even make this simpler by putting, well, I shouldn't say simpler. We could make it shorter by putting the second index plus plus in there. There's a reason why I'm not going to do that. The reason is readability, right? Like, remember that if you put a plus plus here, it's going to increment the second index before it executes the rest of the statement. If you put it here, it's going to do it afterwards. But the good news is that you can just do it this way. 2 lines of code. I promise you that the assembly language and the machine code that's made out of this is identical to doing it this way and getting rid of this next line. So, ooh, what have I done? Oh crap. I hit something. How do I get out of this? Okay, there we go. Okay, I was a moron. I must have hit the hotkey for magnifying glass. Alright. So, now that I'm back, this is how this works. So, we're not going to do it this way. You know, I know that, well, maybe you guys aren't quite as into all that stuff as people used to be. I promise you that, you know, back when I was in my CS degree, that was like the kind of thing people always wanted to do. It's like, we could make this like entire program into one line of code that no one can read, right? And so, you know, it was bad. So anyway, so the good news is, once we get through this while loop, one of the lists is going to be used up, right? Meaning there's nothing left, but we don't know which one it is. And the actual answer is who cares, because we can actually just do this. And it doesn't matter because if, oh, I'm sorry, we don't want to start at 0, we want to start at the first index, right? If the first index is the one that's out of range, then it's just not going to care anymore, right? It's just going to skip this for loop, which is exactly the same as putting an if statement into check. So this is one little bit of, you know, trickery that I will actually do. Result list dot pushback first list. Looks like somebody's home. And then we can do this with J, second index, first, and then we do second list dot size, and we do J++. And then here we're going to do second list, J. And so you might think like, wait, one of these lists is never going to do anything, but the good news is that it doesn't matter, because one of the indices is already going to be at the end, so it'll just skip one or the other of these for loops. So basically only ever one of these only ever one will run. Only one will ever run. That's a little bit better English. So it's okay. The other one won't enter because you know, the indices are, what would we say about the indices? The indices are already past the length. Okay. Cool. So now let's actually implement Mergesort. So remember what Mergesort is doing, right? So Mergesort is going to split the list into two sublists, and then it's going to send it into the then it's going to call Mergesort. So the first thing we're going to do is get a vector first list here, vector int second list. I don't think there's a way. So in Python, there's a nice slicing notation that you can do, but here we're just going to do it in a stupid way. List to sort, so we'll do list to sort.size. And then, okay, there we go. And so what we're going to do is, well, actually what we can do is do something slightly smarter. We can do that. And then we can just stick everything into the first list dot pushback, list to sort I. And then here what we're going to do is shove everything else into the second list, right? This is the part we're not thinking about. So we're just saying unsigned int J. Oh, and it's going to start at the list size over 2. And then we're going to go up to, we're going to scan up to list to sort dot size J less than this, J++, and then we will push back this into the second list, right? So in Python, this is really 2 lines of code, because you can just do something like, first list equals list to sort, something like 0 up to the length of list to sort divided by 2, right, using integer division, and do the same thing for the second list. So this is the Python version, which is always, which is nice and really make it short, but unfortunately with C++, I don't think Vector has any functionality to do this for you, so it'd be nice if there was a slice. I don't think Vector has a slice. Anyway, so once you've done this is basically just doing this slicing business. Once you've done this, what you got to do now is run Mergesort on both of the parts. So you run it on first list, you run it on the second list, and because we're sticking them in like that, what we can do is say first list equals Mergesort of the first list, second list equals Mergesort of the second list. So now we're taking the return values. Why is it not like this? Because it recurses infinitely. It actually detected that. because we haven't put in a base case yet. But whatever, I'm ignoring that for now. We don't. So you notice that this thing is going to go forever because, well, for many reasons. Anyway, doesn't matter. Now the last thing we want to do is merge the first list and second list together, and then we'll just say vector int result equals this, return result, like that. In fact, we could be even smarter and just return the merge, like that. And that's I don't think that's too much of trickery to do. But as cline is telling us, cline is yelling at me because it's saying this is recursing infinitely, and it's true. It is recursing infinitely, and the question is, why is this recursing infinitely? And the answer is because we don't have any base cases, right? Like in Quicksort, I tested to make sure that the size of the list wasn't less than, say, 2. Right? So if list to sort dot size is, say, less than or equal to 1, then what are we going to do? And then we'll have an else, right? Else is do this stuff. Well, actually, we don't even need the else because we're just about to return. There we go. And so basically, this will prevent infinite recursions. And the reason why it prevents infinite recursion is because as soon as we get down to a small enough size, it's going to say, okay, well, either you have an empty list or you have a list of size 1. I think that you can all agree that, you know, a list of size 0 is sorted, and a list of size 1 is actually sorted, right? Because there's only one element, so it doesn't really have any relation to any other element, so you're good. And so that's kind of, so this is merge sort. So all of this stuff here is just splitting the list, right? Here. Then we call the two merge sorts, and then we return the merge of the operation. And this just makes sure that we don't go on forever, right? So, okay. So let's test the merge sort now and see how fast it is before I engage the magnifier again or something. Test merge sort. Okay, and then here we're going to do merge sort. Actually, you know what? Let's do it this way. We'll do test sort. And I know I didn't have enough time to do it last time, but let's make a function pointer. So let's type def, say, what is it, vector int sorting function, and the thing will take a vector int reference. That should work, right? Maybe. Okay, it doesn't like this. I think it's some parenthesis issues. Must be an identifier. Let's see if this fixes it. Okay, that fixed it. It didn't like the parentheses. I can never remember exactly how C++ likes it. There we go. So now we can just test out the sort. We don't need to write individual test sorting functions for each one. What's the problem? Why don't you like it? Oh, because we need to put in merge sort here. Still doesn't like it. Let's see, does this fix it? It does. See, It's all about the parentheses with these function pointers. It's so finicky. Okay. So let's put that up at the top. Cool. But anyway, now that we have that, we're in a happy time, because now we don't have to rewrite this test sort. We can just put the new function in every time. So, okay. So let's run it, and so hopefully this will run on Mergesort, and we'll see if I've coded Mergesort correctly, or if I have any bugs, and we'll also see if see what the average runtime is for Mergesort on various sizes. So this is 100, 1,000, 10,000, 100,000, and 1 million. So this is good. Let's see what happens. Okay, I would like to see the output, please. Okay, so what should take around 10,000. Okay. So I think if you remember that this is all measured in milliseconds, so it's hard to. I wouldn't trust anything that says 1 or 0, because basically if it says 1 millisecond, then it's essentially saying, though I think it's something close to 1 millisecond, but I think it could be anything less than, say, 1 millisecond, bigger than maybe a half a millisecond. So that's why just saying 1 is a little bit hard to understand. But then here we have let me just shut off Steam. Okay. Sorry, I was getting about a message per second, and I was finding it hard to concentrate. Okay. So we see here that there's about a 10 times slightly worse. Well, actually, here it's a little better, and here it's a little worse. Let's run it again and see if there's any. Wow, that's almost perfectly 10 times. And then let's see what the 100 times is. Or 1 million elements. Slightly worse. So this took about 11 seconds. This took about a second to run on 100,000 elements. This took, 0.1 seconds, 0.009 seconds, and then finally 1 second. And so 0.009 to 112 is about an n log n relationship. This is almost over n relationship, so that's actually much faster. But anyway, so the point is here. So this is the experimental runtime, right, for Mergesort. And so let's talk about the asymptotic analysis of Mergesort. So now let's analyze Mergesort, right? So here's the theoretical analysis. So basically, it's almost the same as Quicksort, only it's actually a bit easier, because we don't have to worry about this parameter here that we don't know, because here we had to care about what we fed into the time for Quicksort. So basically, really what we were saying here is like the time of n is equal to about O of n plus 2 times the time of n divided by 2. But the thing is, we didn't know that this was n over 2. It could have been n minus 1, right? Or anything between there. And so that's kind of the issue, is that we don't know exactly what this thing is going to be. So in Mergesort, as I was saying, right, we always split it into exactly 2 lists of equal size, which means we're happier, right? This is happy time, because what it's going to do is it's going to guarantee that our runtime is pretty much fixed. It can vary slightly experimentally, but it's basically fixed for any list. And the reason why it's basically fixed is because splitting in half and splitting in half and splitting in half, it doesn't, the only thing that matters is that the initial size of the list. So what's going to end up happening is we got the time based on a list of size n is equal to, this is approximately the time that it takes to split plus the 2 times the time that it takes to run merge sort, right, on size of n over 2, not n minus 2, n over 2, plus the time that it takes to merge back, right? So we know that the time that it takes to split is approximately O of n, because why is it O of n? Because it has to scan the list once, right? And that's an O of n operation, right? It has to scan the original list once. And T of merge is O of n for the same reason, right? We're taking 2 lists of size n over 2 that are pre-sorted and making a sorted list, which means we have to basically scan through both of those lists at least once. And by at least once, I mean exactly once. So basically here we have O of n, all right? And so that's the best and the worst case performance. So when it's best and worst case, we don't always use O of n. Sometimes we use theta of n. And I'll explain what theta of n means in just a bit, but you can just call it O for now. It's okay to call it just O. So the only thing we have to do that's left over is just to figure out the number of times that this thing is going to recurse, right? And so if you remember the calculation we did last time in the best case of Quicksort, so the best case of Quicksort, Quicksort says that the number of steps is basically the log base 2 of n. And it's the same in our case, right? Because if you split something in half, and you ask how many times can I split something in half before I get down to single elements, the answer is 2 to the number of steps, where the 2 to the number of steps is approximately equal to n. And so we need 2 to the number of steps to be approximately equal to n. So we take the log base 2, so steps is approximately equal to the log base 2 of n, which we just write as lg of n. And so basically here, what we have is that the time of based on n, right, is equal to O of n plus 2 times the merge sort on n over 2, which is actually going to be technically what it is going to be O of n over 2 times log of n over 2 or something like that. But again, the constants are all going to absorb, plus O of n. And so O of n plus O of n is equal to O of n, right? Because it absorbs a constant c. Maybe I'll have you prove that on some homework, right? That's like a good problem. And then O of n plus O of n log n is actually equal to O of n log n. And that finishes up our analysis, right? Our analysis is complete. So this is both the best case, the worst case, the average case, all the cases. And the reason why it's all the cases is, as I say, Mergesort does not care about the structure of the list. Mergesort is just going to hammer away at it in the exact same process until it's done, right? In no part of our Mergesort algorithm did we, well, I guess in the merge part we did, but the point is that the merge part always is going to run exactly the same. Mergesort and Quicksort are kind of duals in a sense, because in Quicksort you split based on the order of the elements, right? And in Mergesort you merge back based on the order of the elements, and you do that after, right? So in Quicksort you split things up first, whereas in Mergesort you split up the lists but you don't do anything to their structure. Then you sort them, then you merge them back. But in Quicksort, basically the merge thing is like we anti-do the merge, and then we sort them both using Quicksort, and then we remerge the last 2 parts. But merging in the last 2 parts is a different thing in Quicksort, right? So merging in merging here merging is actually putting things in order. In Quicksort, merging is just sticking first list plus second list, right? That's all it's doing. It's not actually, which is exactly what we're doing here, which we're doing the split operation. So I never really thought about that before, but yeah, no, it is actually true that Mergesort and Quicksort are kind of, it's like the same kind of process, it's just done in like a reversed sort of order. So I think that's kind of an interesting thing to think about. Okay. So cool. Now, as I say, if you pull up like a Windows calculator and you just plug in some numbers, let's say we plug in, you plug in, say, 100,000 times the log of 100,000, right? And then you divide that by, say, like 1,000,000, or say 10,000. Let's do 10,000 divided by the log of 10,000. Oops. It's very hard to do with Windows Calculator. Maybe I'll do it with something else. What's better than Windows Calculator? Maybe Wolfram Alpha. It's probably better. And also you'll be able to see here, and I'm not sure why this was in my autocomplete results, but this was in my autocomplete results. I guess I was testing out to see what was going on here. So, okay, say 100,000 times the log, well, say log, oh, you can do log 2 of 100,000 divided by, say, 10,000 times the log base 2 of 10,000. And hopefully this gives us something meaningful. I think it was going to give us 12.5, which is great. So what does this 12.5 number mean, right? What does it tell us? What it tells us is that as you increase, right, what does this 12.5 number tell us? It tells us that as you increase the number of elements in the list by a factor of 10, you expect that the runtime is going to increase by a factor of approximately 12.5. Now here you actually see that it was a little bit better than that, and I'm not 100% sure why it was actually a little better than that, but it is a little better. I think it probably has to do with the, as the size of the list grows, probably there's not as many allocations down at the bottom, so there's probably some like experimental factors based on memory allocation that cause this. You see it's a little worse. In here we get 112.7, here we get 114.8 in terms of our runtime. So this is a little worse than 10 times, which is kind of showing what I want to show. I think we would need to like force a 64-bit compilation so that we could use multiple gigabytes of RAM in order to actually get the required performance. And I'm definitely not going to try to do that right now, because let me promise you that the more you try to mess with compiler flags, the more hours you're going to waste. I think this is just compiled in like a 32-bit mode, so we can't go much higher than 1 million elements. I tried to go to 10 million and it seg-faulted. It wouldn't let me allocate 10 million elements. But generally also, they are not going to run any of your algorithms on anything more than, say, 500,000 to 1 million elements anyway. And the reason is exactly this, because once you compile it, if it's in a 32-bit mode, it's not going to be able to handle 64-bit pointer size and all that stuff. So anyway, but the good news is all of those kinds of details are the things that Big O does not care about in the slightest, right? Algorithmic analysis doesn't care about any of that. It gives us a number. It says expect about 12.5 and 10 here, and then a little bit more like, I don't know, 10 point something here, and it's close enough to 12.5 to not be ridiculous. Remember that our runtime estimations are always kind of approximated. We can always, the difference is usually between a factor of, say, 10 and a factor of 100 when you increase the input size, right? Like the quadratic sorts, and let's do another quadratic sort. So let's do a insertion sort, vector int insertion sort. And here is a vector int reference list to sort. So how does insertion sort work? Insertion sort, the way I think about it, and I always used to forget when I was a student how it worked. I don't know why. Well, I do kind of know why, but it doesn't matter. So insertion sort, I call it the is equal to the pullback sort. And let me show you why I mean that. So what you're going to do, and let me find the sorting algorithm thingy, and then we'll play an example of insertion sort for you. Let's see, is it here? Here. No. Let's just load it up again so I don't have to find it. Okay, I think. Oh, got it. Here we are. So let's go to insertion sort. And then I'm going to run it, and I want to argue why I'm calling it pullback sort as well. Pullback sort is just what I call it. It's not an official name, but it helps me understand, because selection sort also inserts things into the correct position. And so to call it insertion sort is not actually describing exactly what it's doing. Whereas like selection sort is like the find min sort. It goes to the list and finds the minimum each time. I think insertion sort is really the pullback sort, and here's why. Here we go. So what it's going to do is nothing there, nothing there. Oh, I'm sorry. That one was 38, not 48. What it does is it drags an element back. See, it's dragging this element back or pulling it back until it's in the correct position, right? So it's going to drag this element back until it's in this position, and then it's going to stop. It's going to drag this element back until it sees 26, and then it knows to stop. And then I'll explain exactly what it's doing. So here it's going pretty fast here. So here it's swapping all these elements, pushing them all up, and then pulling this one back. So there it goes, and then here we are, 46. We'll put it in there. 4 is going to come all the way back to the start, and then we just have a few elements left. Maybe I'll slow it down because there was no way I could say anything meaningful while this was happening. But yeah, so this is why I call it pullback sort, because it picks an element and it pulls it back into its correct position, and then that's what it does. So here it's going to pull this element back 1, and then here it's done. So what's going on here, right? Let's create a new random list, and then we will sort, and I'll slow it down so that I can kind of describe it. What it's going to do is it's going to look at the second element first. Really, you could say it looks at the first element, but it doesn't. It's going to look at the second element and it's going to ask it, are you bigger than I am, right? And if you are bigger, then I'm going to shift back, right? So here it's going to say, it's going to take, well, okay. There, it takes 16. It's bigger than 30, so it shifts it back, right? Also have to shift 40 up. So then here it takes 49 and asks, are you bigger? And the answer is no, so it leaves it in its current position. What you notice about insertion sort is that at every stage up to the current position, the list before it is sorted. The list after it's complete garbage, but the list before it is completely sorted. So as we continue here, it's going to take 2 and it's going to say, are you bigger? Yep. Okay, I'm going to swap back. And then it's going to say 30, are you bigger? Okay, swap back. I'll speed up just a little bit. There we go. 16, are you bigger? Okay, pull back. Here, it's going to take 49, it's going to pull back 1, but then it's bigger than 30, so it's not going to pull it back. 22, it's going to go all the way back to 16, pushing the other elements forward. So let's increase the speed. Here's a bunch of 31s. With the 31s, it's going to pull them back, and it's going to do this. With 2, it's going to pull it all the way back to the start. 27, it's going to pull it back to right there, between 22 and 30. So this is actually kind of, I shouldn't say this is the worst case, but this is one of the worst cases of insertion sort, because you have these elements that need to go all the way up to the front, that are stuck in the back. Okay. So let's do this then. Let's actually code it up. So how do we code insertion sort? So we're going to do a for loop for, say, unsigned int I equals 2, or I guess actually 1 because it's 0 indexed. I is less than list to sort dot size I plus plus. Okay. So that's the uninteresting part. That's the part that we see in the vast majority of sorts, at least quadratic sorts, and insertion sort is another quadratic sort. Sorry to spoil that surprise. But this time, we're not going to do another for loop. We're actually going to do a while loop. We're going to say while the element at I, right? So list to sort at I is less than list to sort at I minus 1. Now, you might, actually, we should rename it. So, int current equals I. So now we'll have current here. There we go. That's better. So the first thing we have to do is make sure we're not in an infinite while loop. So we're going to do current minus minus at the end. And then here, what this is going to do is it's always checking to see if the thing at the current position is less than the thing at the previous position. If it is less, then we know we need to swap it. So we're going to swap list to sort at current with list to sort at current minus 1. And this actually works, so we're in good luck, right? It's going to swap these two things. And so basically, once it swaps them, then we'll just decrement our position and move back. So this is the pulling back part. Okay. Oh, should be unsigned. Doesn't. It's the annoying thing. And then, so this is, if you notice that this is an in-place sort, right? Because everything is done in the same list. We don't create any temporary lists like I did for... So there are in-place merge sorts, there are in-place quick sorts, there are... so selection sort is an in-place sort because it does swap. Insertion sort is an in-place sort because it does swap. The versions of quick and merge sort that we did were out of place in the sense that they didn't put things... They didn't just swap elements, they created temporary lists. But it is totally possible to make a quick sort that and a merge sort that go in place. And we can return, we can just return the same list to sort. So technically we could even make this void. We don't even need to make this return the thing. Like that. And then we can, let's run a time test on this thing. Let's see, how do we run a time test on it? So we change this from merge sort to insertion sort, like this. And hopefully we don't get an error. No matching function call, because it's because of this reference. So I'll just take that out. It doesn't matter in the end. At least not for our time test, so it's okay. Okay, so let's run the time test on it now. And then we'll think about best and worst case stuff. So hopefully it runs. Ooh, wonderful. Oh, I'm sorry. We need that. Otherwise, this will just be an infinite loop. Let's use that just because we feel more C++-y. And let's see, what's the other syntax error? Man, it really didn't like it when I did that. Okay. Let's try to build it again. Okay. Vector subscript out of range. Interesting, it didn't like that. Getting errors on it. so I guess we can debug now. So let's debug this stupid thing. Why is it? Oh, of course you would say, well, did you check that before you then stuck it in, like some kind of idiot? I didn't. I didn't check. There we go. Okay, so while that's going, and I promise you it's going to be uninteresting because it's a quadratic sort, you notice that it already took 100 times as much time here as it did here, and it's hard to tell with this one, so we'll just move on from that. So let's talk about the runtime in the last few minutes of class. So let's do our analysis of insertion sort. So let's actually talk about the worst case first. So the worst case is an unsorted list, right? And the reason why it's an unsorted list, actually the worst case is basically a reverse sorted list, which is also unsorted, but it's closer to the average case. So let's talk about it first. So what does a reverse sorted list mean that we have to do? So basically, let's look at our little diagram, our little visualization, and I'll show you what a reverse sorted list is going to do to us. So let's create a list. Let's make it 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Right? Create this list, and then let's sort it. So what's going to happen? The first thing that's going to happen is that this is going to have to swap, then this is going to have to swap twice, thrice, 4 times, 5 times, 6 times, right? 6 swaps, 7 swaps, 8 swaps, and finally 9 swaps. So you see what we're in again, right? What happened here is basically a Gauss sum of swaps, right? Where we had 1 swap, then 2 swaps, then 3 swaps, plus 4 swaps, plus 5 swaps, plus all the way up to technically n-1 swaps, but not gonna help you much, right? We add them up, we get n times, I guess it's actually n-1 times n divided by 2, which is O of n squared. So the worst case for this algorithm is O of n squared, and we see that happening in real time right here, right? Because this one on 100,000 elements is 68,000 milliseconds, which is 68 seconds, whereas this one only took 0.6 seconds. So this is, again, approximately 100 times worse than the previous one, right? So this is giving us justification for why we would call this a quadratic sort, because if you did these two numbers divided by each other, right, you do 68,652 divided by 685, you'll get about 100, right, and 100.22, and the thing is that you know that if you took the square root of that, you would get the size that we increase the data by, approximately 10. So that's why you call it a quadratic sort, because if you take the 2 times and you divide them, then those times are the square of the elements that you've added. Okay? So that's that, and then I guess the last thing to say is let's just talk about the best case really quickly. Best case of insertion sort. And then the last thing to say, actually before we talk about, well, okay, let's talk about the best case of insertion sort. The best case of insertion sort is when the list is already sorted. So instead of being that, we can do something like this, and then we sort it. What you're going to notice is this thing only does one check, right? It only does one check every time we go through the insertion sort, which means that instead of being 1 plus 2 plus 3 plus 4 plus 5, it's actually just 1 plus 1 plus 1 plus 1 plus 1 plus 1 all the way up to 1 n times, right? And so that is just O of n. So interestingly, the worst case is O of n squared, but the best case is just O of n. And so this is why insertion sort is actually used for a lot of different applications because it has a good best case, and in lists that are relatively sorted, so in lists that are more sorted than not, insertion sort is actually pretty good. In lists that are generated to be very, very random, not as good, right? Because this is going to basically our expectation here is that this took us 68 seconds, which is about a minute. So our expectation of the next thing is that it should take about 100 minutes, right? So if it's taking about a minute, this should take about 100 minutes, which is like 1.4 hours or something like that. So it's going to take a long time. Or actually, it's closer to like 1.7, 1.66 hours. So I'm going to let this run and see if it ever finishes or if it seg faults or something like that. But if it does, it should finish in approximately 2 hours. So basically, if we started this program as soon as the lecture started, it would still be going now, and it would have another 20 minutes to go. So that's why we don't generally use insertion sort or selection sort or bubble sort, which I haven't really taught, but is another quadratic sort. We don't use those sorts on any lists of large size because obviously that would be very bad. Okay, the last thing to say is that for submission to our classroom, I've opened a GitHub and I posted the link to, it's a GitHub classroom. So what you do is you go on there and then you find your username. So go on the GitHub link, find your UMBC username, and then you should be able to basically drag and drop files into the GitHub classroom, and then it will submit them to me. Now I'm going to try to see if I can run some tests. I haven't been very successful in the last semester. I'm going to try to make it work a little better this semester. So that's on my end. If not, I'll just read your code. So either I'll just read your code, and so that means slight mistakes will not be noticed, probably. Or I'll try to compile your code. Maybe not for this, probably not for this assignment. And I'm going to allow you to submit everything. I'm going to give you an extra day or two just because I know that the GitHub hasn't been up. So if you're having any trouble with the GitHub link or anything, you can, if it's on Thursday and you really, really just want to submit it to me, you can send it to me by email. But I'd really prefer that you try to get the GitHub to work because I'm going to try to use it for the rest of the assignments for the semester. And I'll try to make it more interactive, as in we'll run automated tests there on your code. But I think in order to do that successfully, you would have to actually have like a 99% working project, and then you'll just implement like one function for homework. Whereas in this case, your homework is to implement an algorithm, and there's no way for you to know if the implementation that I do would work with yours, you know, if the functions have the same name, or if it's length versus len versus whatever. All of those things would cause nice compiler errors, which would prevent anything from working. So we're not going to try to compile your code for this assignment. I will just read your code, but just questions 1 and 2 on GitHub. So the rest of the stuff should be submitted on Blackboard. So only code to the GitHub. Unless, I guess technically we could use the GitHub for everything if you upload the PDFs there. But currently, just for this assignment, submit the written work to Blackboard. Maybe it's a good idea. We could change it in the future, but that's what I was doing last semester, so that's what we'll do for homework 1. And yes, I want a PDF on Blackboard. It's not a bad idea. I think it's actually something that we could transition to, but just because this assignment, I had the submission link open on Blackboard for so long, I think it's good if I just keep everything on Blackboard that's on Blackboard, and the code goes to GitHub, right? Code goes to GitHub. PDF goes to Blackboard. All right. Okay, so that's it for now. I think hopefully this was a understandable lecture. Hopefully everybody thought that Big O was really easy. It's okay if it's written out as long as it's legible and just convert it to a PDF. Is the exam next week? Let's look at the syllabus and look at the times. Oh wait, this is the syllabus from last semester. No. No. Our first exam is going to be after we cover trees. So we're going to do... So the first exam will cover like linked lists, stacks, queues, decks, and then it's going to cover trees, and maybe AVL trees and splay trees. And so the point about that is that in order to cover all of that, so our first exam will happen when all of this material is covered. So even if we have to shift it a little bit on the schedule, we will shift it. So, and we did lose about a week of lectures so far. So I need to figure out what to do about that. So yeah, okay. I'll still need to figure out what to do about that. It's possible maybe we'll do a Friday lecture or something like that this week. All right, so I think that's all the announcements I have. I think that's everything. So I'll let all of you go. I know I've kept you too long anyway. So, all right, good luck. Have a good rest of your day. All right.